In this video, I'm going to show you how to use a method of sections analysis to find the axial forces in a truss. The method of sections is a method that you can use if you only need to find a few of the forces in a truss. So say you had a truss and you only wanted to find forces in 3 of the members, or you wanted to find the force in one member based on a function of some applied loading, for example. Or in a classroom setting, basically you get a problem on an exam and they give you a truss and they say find the load in member AB and AD. Then the method of sections would really be the most efficient way to solve that kind of problem, because you don't have to find the forces in all of the truss members in order to find the force in one, which is the case if you were to do a method of joints analysis, which I explain in another video. So the method of sections is like as if you were cutting a beam and you wanted to see the internal forces that went across that cut. So when we do this method of sections analysis, we can only solve for 3 unknowns because there are only 3 equilibrium equations in 2D. So we can only cut through at most 3 truss sections at a time. So I'm going to go through the general procedure, but then I'll do a full worked example so that you can see how it actually goes into practice. So the procedure is that first you want to select a section to cut, and that section that you select obviously is going to depend on which members you want to find the forces in. Now in that section you want to select a section that has at most 3 members that are cut, and that section also has to cut the truss completely into 2 separate pieces. And then after you select that section, you pick one of those cut pieces. Ideally you want to pick the one that has the least number of loads on it, because it will be the easiest to analyze, or the section that doesn't have any reactions, for example. But if there is an external support in that piece that you select, then you have to calculate the global reactions first using the uncut truss so that you can have that external support loading on your section for the free body diagram that you're going to draw. And then the third step is to use a free body diagram of that cut piece to solve for the unknown forces in the cut. Again, 3 at maximum. So I'm going to do an example that is on the tricky side. This is a K-Truss, and in this section you see I've asked, we want to find the axial forces in members AB, which is this one, AD, DF, and FG. Now here there are 4 that we want to cut, and there's really nowhere in this truss that we can cut it just into 3. So really the cutting method of sections problem where you cut only 3 members is kind of a trivial problem. So I'm doing one here that's a little bit more tricky and relies us to rely on a kind of special trick in the method in order to deal with a situation where we have 4, such as this K-truss. This is probably the most complicated situation that you're going to find in practice. So we have this truss, it's a K-truss, and we want to find the forces in these 4 members. So how do we get started? This is, first of all, this is a determinant truss because we have only 3 reaction points here. And so we want to, we want to find the axial force. So first thing that we're going to do is find the reactions. You can never really go wrong doing this first. It always gives us some sort of extra information. You see, we're going to have to cut somewhere here, obviously, so no matter which side of the truss we're going to use, we're going to have one reaction. So let's just find the reactions first. So let's do a sum of moments about point J, which is the left reaction point here, equal to 0. So these are 4 meters apart, these nodes. So the first one is -10 because it's clockwise, times 2 times 4 is 8 meters. That's this one. Then -10 because it's clockwise again, times 12 meters. That's the difference between here and here. And then the reaction, the vertical reaction at I, which is IY, times 24 meters, which is the entire length of the truss, equals 0. And if we solve this equation for IY, we get IY equals 8.33 kilonewtons. Well, this is the only one that we're really going to need in our analysis, but just in the interest of completeness, I'll find the other two as well. So we have Fy equals 0. So here we have Jy, which is the reaction at the left side, minus 10, minus another 10, plus 8.33, because our reaction at the right side goes up. And we solve this for Jy. We find that Jy is 11.67 kilonewtons. And then sum of Fx is trivial, because we only have one force in the x direction, which is Jx, so Jx is equal to 0. Okay, so our next step is that we want to select our section. Okay, now you see the selection that we'd like to use, here I'll draw it in blue, we would ideally like to use this section here and call this AA. Okay, but there are 4 members here, so I'm going to write this down here. Okay, we'd like to use AA, but there are 4 members, which we learned on the previous page is too many for us to do a sectional analysis. So what we need is to find a way to find one of these. To find one of these forces before we do the main sectional analysis. So what we need is to find an additional section. Oops. Or an additional cut that, okay, that satisfies these two conditions, okay? First, it has to include one of the members that are cut by AA. And the reason for that is that we need to find the force in that member. So we obviously have to include it in the second section. So we're trying to reduce the number of unknowns in section AA by finding one of the forces ahead of time using an alternate section. So this is what we're doing. So obviously that alternate section has to include one of those members cut by AA, which is the one that we want to find. And then B, all other members at the cut are, all the other member forces at the cut are concurrent through a single point. And I'll show you what that means. Okay, so let's take a look here. Okay, so up here we want to make a cut where the members that are cut include one of the ones from this cut, and all of the rest of the forces from the other members are concurrent through a point. So I'll show you which one works here. So if we cut like this, okay, and we call this cut BB, okay, this member here, AB, is in common for both cuts. So this is the one that we're going to solve for in order to reduce the number of unknowns in AA to 3. Now the other 3 here that we've cut, this vertical one BD, this diagonal one GE, and this horizontal one GH, if you draw lines through the forces for these, they all go through a single point G. So if we were to take a moment equilibrium about G, these 3 forces which go through G would not come into play in the moment equilibrium, and then we would only have the external force, Iy, and the force of the member that we're trying to find as the unknowns. So we would have one equation and one unknown, and we'd be able to solve for AB. Then that force AB we can bring into the section cut AA, and that means that we only have 3 unknowns left, which means that we can solve for the other 3. And if that's not clear right now, then it will quickly become clear as we continue the example. So we select section BB, because, not to belabor the point, but A, it shares member AB with section AA, and B, the other cut members which are BD, EG, and GH, if you refer back here, BD, EG, and GH, are concurrent through point G. All right, and so that's all that the trick is, and once we know that trick, then we can solve this problem. So let's go for BB. We're going to look at this section cut, so let's draw it. Okay, it's going to look something like this. Okay, so here I'll draw that cut again. Okay, so that cut looks something like this, right? So it came across this vertical section as it went down. So now if I draw all of the nodes, this one is B, C, E, H, and I, and then there's also G, which is not a point that's included in the cut, but is a geometric location that still exists. Okay, then we can draw all the unknowns. Okay, this is FAB. Okay, so that's the unknown axial force through this section. This is FBG. This is FEG. And this one is FGH. And then we also have IY, which we also already determined is equal to 8.33 kilonewtons. So now, if we do a sum of moments about G, okay, equal to 0. Now, you might think we can't do a sum of moments about G because G is not in the cut, but as I said, G is just a location. Okay, so this is a convenient location to do our moment about because all of these forces go directly through that point, which means that they can't cause a moment about that point, right? So this is just a point in geometric space here, G. Okay, and this is a general tool to use when you're doing section cuts using the method of sections. You know, don't be afraid to use points that are outside of your section. Okay, so now if we do this, all we have is FAB times 6 meters, which is the height of the truss. Okay, then plus 8.33 times 8 meters, which is the distance between G and I. So that's the horizontal distance. So you remember the moments are always the force times the perpendicular distance between the point and the load. So in this case, it's the perpendicular distance is in this direction, and in this case, the perpendicular distance is in this direction, equals 0. So if we solve this for FAB, then we get negative 11.11 kilonewtons. So that's 11.11 kilonewtons compression, C. Okay. And we know that's the case because I assumed that these forces were in tension, right, which means that they pull away from the member. But since we got a negative number here in our result, then that means that the arrow that I drew originally was in the wrong direction, so it has to point in, which means that it's in compression. That's actually in compression. So now we've used that to find AB, and you'll see none of these came into this moment equation because there's no lever arm, because these points go right through G. So now we can go back to AA, and now we solve this just as if it was any other method of sections problem. So let's draw the full section again. So this one looks like this. There's this piece, this piece. This is a bit crooked. Just imagine the XY axes are a little bit skewed here. Okay, so now this entire K piece is within the truss. Let's draw that one again. Okay, and let's shorten this a little bit. And we've got these 4 members are cut here. So let's draw all our points in here. We have B, C, D, E. This is G, H, and I. Now again, we're going to want to keep A and F as geometric points within our section. So those points lie outside of the section, but we're going to keep them anyways on our drawing. And this is where our cut is. This is cut AA, right? Okay, so then we have some forces. This is IY again, 8.33 kilonewtons. Okay, and now we've got 11.11 kilonewtons. This is AB. So this is the force that we solved for when we made this secondary cut BB. So we know that that's in compression, so it points at the member. It wants to squish this little member here. And then I'm going to draw unknown forces for the rest. And I'm going to just assume that they're in tension for now. So this is FAD. This one here is FDF. And this one here is FFG. Okay, and these are inclined, so they have some angle theta. And that angle is the same because this is halfway between, this node is halfway between the top and the bottom. Okay, so let's do sum of M now about F. So why do I want to choose that one? Well, so if I choose a moment about here, these 2 unknowns go right through that node, which means that they're not going to come into the moment equation. This one we already know from the other section, so that leaves us with only 1 unknown. So we're going to be able to solve this one right away because we have 1 equation and 1 unknown. Now the geometry for this one is a little bit tricky, so let's draw it out. First of all, let's find that angle. Theta is tan negative 1 of 3 over 4. Because the height here is 3, that's half the height of the truss, and the bay width here is 4. And that equals 36.9 degrees. Okay, so now if we look at points, if we have A like this, and we have F down here, okay, and we have FAD, which looks something like this. Okay, and we want to draw a little triangle here. Then we want to find out what this dimension is here, which is, so we're doing some moments about F. We have FAD, which does a counterclockwise or positive moment about F, but we need to find out what the perpendicular distance is between FAD and F. Okay, so we know that this angle here is theta. Okay, so that means that this angle here is 90 minus theta. Okay, because this is 90 overall, right? This is a right angle. And so that means that since the sum of the angles in a triangle adds up to 180, and this is 90, and this is 90 minus theta, that this angle is theta. So therefore, okay, so this total height is 6 meters. Okay, then the total distance here is going to be equal to 6 cos theta. Okay, so that allows us to get our moment from FAD. So if we continue with the sum of moments about F, and counterclockwise is positive, then we get negative 11.11 because that's clockwise, which is negative, times 6 meters, which is the perpendicular distance, the full height of the truss, plus FAD, the value of that force, times 6 meters times cosine of theta, and theta is 36.9 degrees, plus 8.33, which is the reaction, times 12 meters, which is the distance between F and I, equals 0. Okay, that ends up, if we solve for FAD, we get FAD is equal to negative 6.94 kilonewtons, which means 6.94 kilonewtons in compression, because we assumed that it was in tension to start. Then the rest of the truss is trivial. We do sum Fy equals 0. So we get negative 6.94, okay, times, this time the sine of 36.9. Okay, so that's FAD. In our drawing, FAD goes up, which means that it's positive. But if we assume that it's positive, the sign of the value is negative. So that's why I put a negative in here. Alternatively, we could switch that arrow around because we know it's in compression and just say this goes down, therefore it's negative, therefore we get negative 6.94. And then negative FDF, which is pointing down as well, times sine of 36.9. Okay, because it's the opposite force component using this angle, plus 8.33 equals 0, and that gives us FDF is equal to 6.94, and since that's positive, it means it's in tension, which is what we assumed. And then last step, we do sum Fx equals 0. To the right is positive. We get now negative 6.94 times cos of 36.9. Okay, so that's FAD again. So we've assumed that it's in the negative direction when we drew it. So that's where this negative comes from. But then when we solved for that force, we got a negative. So that's where this negative comes from. Alternatively, as I said, you could turn this around and point it in the direction that it actually goes, which is in compression. And then you would know for sure that the arrow is pointing to the right, which means that it would be positive. So we either get a negative times a negative equals a positive, or we switch the direction of the arrow and we get a positive just from the geometry. And then we have negative 6.94, which is from FDF, and we know that that points in this direction, so it's negative, which is to the left, times cos of 36.9, and then all of that plus 11.11, which is FAB equals 0. So then we solve, and I forgot the unknown, which is negative FFG equals 0, and that's this unknown here. So FFG equals 11.11 kilonewtons, and that's tension because it ended up being positive. And so that's all the forces that we wanted to solve for. We didn't have to solve for all the rest of the members in the truss. We had to use this little trick in order to eliminate one of the unknowns, since this is a K-Truss, but otherwise pretty straightforward sectional analysis problem, and that's how you do it.